I'm Sam Lerma. I'm a first-time speaker here at PyData NYC. And so my talk today is graph analytics from the Whiteboard to your Toolbox. So in case anybody wandered in without reading the abstract online, here's a little bit about what you can expect over the next 40-odd minutes. There's really three big parts of this. So the motivation was I was studying graph theory on its own for a long period of time and became fascinated by how many different problems you could apply it to and how great it is to work with it in Python. So I'm going to cover some basic principles of it. If you've had any sort of formal training in it, that'll mostly be a refresher. Then I'm going to run through some basic scenarios you might see, and we're going to talk a little bit about how you could express it as a graph. And then I'm going to tell you some of the tools available for working with graphs in Python and show you some code snippets that we can talk through. So this is a novice level track, so I'm assuming no background on your part beyond high school math and that you're familiar with basic Python syntax. So the goal of it is basically for this to be a jumping off point for you to go deeper on your own if you think it's interesting. So don't worry, I'm not expecting you to commit these to memory. But basically the reason I wanted to show these longer definitions is a lot of the material on graph theory for its own sake is written specifically for mathematicians. And there's no universally agreed upon terminology for everything. So it can make it particularly confusing if you're sort of coming in without a strong math background and you're not used to formal definitions and proofs and things like that. So whenever I'm teaching on it, here's usually the definition I give people, which is this is a graph. I call it the ball and stick model. We've got A, B, C, D, 4 balls, and we have 6 sticks between them. So right here in the middle, if you ever see 2 cross each other without anything, think of it as over-under, right? They're not interacting. So if you can come up with a way to explain it in balls and sticks, it's probably a graph. So going through a little bit more of the terminology here, we have 2 vertices connected by an edge. One thing I want to make clear is some people will say node. Usually, especially if you're working with people in the software community, they're going to say node. So when I'm talking about the pure stuff, I'm going to say vertex, and then I'm going to switch over to saying node once we get into the code. I might let it slip one way or the other, so just be forewarned. So if we have 2 connected like this, we say they're adjacent. So adjacent vertices means there's an edge between them. When I'm talking about the neighborhood of a vertex, that means every vertex that is adjacent to it. So if you could imagine a third one shooting out right here, say we labeled it vertex 3, the neighborhood of vertex 1 would be vertex 2 and vertex 3. So let's look at a little bit more complicated one with a couple more things going on, just to sort of get you familiar with some more of the terminology. So up here, we've got this funny edge that goes from A to A. That's called a loop. That's allowed in some cases. You can also see right here, we have multiple edges between A and B. That's also allowed in certain instances. So if I start talking about the degree of a vertex, that's the number of edges going into it. So the way I think about it, if you were to draw a circle, how many lines would you cross? So C has a degree of 3. This loop adds 2 to the degree, so A has a degree of 5. We can also start talking about paths. That basically just means if the edges were streets and you walked from one vertex to another, is that possible? So we can go A, B, C, D without repeating any vertices, so we have a path. We can't get from D to G or anything like that, so there's no path. This right here, too, you might hear me say cycle. That basically just means you can start, follow a path, and end up back where you start. So this we'd refer to as a 3 cycle. Just a couple more things I want to talk about with this. Basically, we can think of this as 2 sets. So this, everything in the white is one graph, but they're not connected. So if you hear me talk about disconnected sets, you might hear people say disjoint sets if they're more in the context of math. I'm just going to say disconnected sets to keep everything as understandable as possible. So you can see here A, B, C, D, E aren't connected to that, so we can split it into 2 sets. One other important concept is a cut vertex. So if we were to remove a vertex, we also take all the edges jutting out of it with it. So going back to the whole drawing a circle, if we were to remove C, we would follow a circle all the way around it, right? You can think of it as following a circular cut. So a cut vertex means if we remove that vertex, we're splitting it into more sets. There isn't one here. Just sort of want to cover this stuff a little bit quickly before we start getting into the examples. So it's also important to talk a little bit about an adjacency matrix. So that's a nice, easy way of representing a simple graph. So if you're looking at the matrix here, we would want to label it left to right and top to bottom with the nodes in a specific order. So going alphabetically here, A, B, C, D, we would step them off from the top, A, B, C, D, and the same way down, A, B, C, D. So this O is this 0 is AA, AB, and so on. So what these lines here represent If there's a 0 there, that means it's not adjacent to the matrix. And if there's a 1, that means they are adjacent. So right here, AA, that's a 0. If we had a loop there, that would be a 1. A is adjacent to B, not C, but it's adjacent to D. So once again, you don't have to remember all this stuff. I just sort of want you to be aware that these are some of the concepts before we start applying them. So this is a digraph. Everything's exactly the same. The only difference is instead of a stick, we've got an arrow. And so when we're talking about paths in a digraph, we have to follow the arrows from one way to another. They're one-way streets. So here's a little more complicated one. This is called a tournament. The only important takeaway point is you can see if we think of these as wins or losses, every vertex is paired with every other vertex. We can also talk about in degrees and out degrees. All that means is an in degree is an arrow pointing into it, an out degree is an arrow pointing away from it. So it's exactly what it sounds like. This is called a bipartite graph. The way you're going to immediately recognize it if it's laid out nicely like this is if you had a pair of scissors and were to cut with one motion all the way across the middle, you would disconnect everything, right? So A through D aren't connected to each other, and E, F, G, and H aren't connected to each other. So one of the important concepts I want to talk about is a matching. So that's if we look at these edges going from one set to the other, can we pair each one from the top set with the vertex from the bottom set without adding any new edges? So in this case, I drew it, so yes, we can. And this is a weighted graph. So the big takeaway point with this is we can store information on edges. So if we're talking about a path, these weights add up as you go from one to the other. So if I'm talking about going from A to B to C, we'd look at the weight of that total path as 0.5 plus 0.4, so it'd be 0.9. So that has some applications for optimization. As you're going to see, we can actually store whatever data we want on edges in Python. And so the last sort of pure concept I want to talk about is graph coloring. We can color vertices however we want. We can also color edges, although I'm not going to go into too much detail on that here. What you see here is called a proper coloring. So if you look here, that basically means no two adjacent vertices are the same color. So the reds are non-adjacent, the greens are non-adjacent, and the blues are non-adjacent. So if you hear me say proper coloring, that just means we don't have two vertices next to each other that are the same color. So now that we've kind of gone through a little bit of the theory, if we're looking at a problem in the wild, what are some signs, right, that a graph might be a good way to think about it? So for me, the first question I ask myself is, am I looking at a set of objects and what I'm trying to find out is the relationship between them or the interactions between them? That's really where graphs shine. We can also think of one object going through different transition states. So right, my background's sort of in the chemical sciences, so one of the big ones we used to do was if you're looking at a chemical going through a process, every reaction is a different state, so we can start drawing graphs. And sort of on that note, when I say orientation, that's basically if we have different parts of a single object and we want to see what happens as we move it, what is graph theory going to shine on that? So once again, with that, rather famously, paraffin waxes have been studied using graphs. Basically, the vertices would represent an atom and the edges would represent a bond. That's all I'm going to say about the chemical side of it. But really one of the valuable things with this is it can cut across quite a few different problem spaces. So a lot of these simple techniques can be applied broadly. So let's look at the first one. So you can see here, this already very much looks like a graph, right? So if this represented, say, Facebook friends, call data, anything like that, right? We have a group of people and we're trying to find out how they relate to each other, or sort of what we can say. So some of the questions we might want to ask here, right? Who's the most influential? How many different people know each other mutually? So if we were to draw it into a graph, right? This one's nothing too crazy. This looks very similar. But a couple of the things that if we're looking back at the concepts I talk about that might stick out. So we have a 3 cycle here, right? So we can see every one of those 3 vertices is adjacent to each other. So if this did represent, say, Facebook friends, we would know that all 3 of them know each other. We can go and count off the degrees. And if you notice, these 2 red ones have the highest degree. So we'd know that they're sort of the most active on there. Some of the other concepts we could put in, if this was call data, we could use directed edges to represent one person calling the other. Or if we were looking at Twitter followers, right? We could just decide which end of the arrows who's following who. So we could start counting off paths. We could start looking at degrees of separation. So particularly like in law enforcement, one of the big things they do is they look at, if you're counting off all these paths, how many degrees separated are people? So that's sort of another big technique you'd want to use if you're looking at a social graph. So here's another one. Actually, my first introduction to graph theory was looking at an e-commerce site. And so we were trying to figure out how we could model user paths through it. So if you're have information like this, right? We have different pages. We know who viewed what page and when. How might we come up with a graph to represent it? So for me, the first thing I thought of was the pages are obviously going to be vertices. So then the question becomes, is there any information we want to store on the edge? What type of edge is the most explanatory for this? So if we consider a simplified case, this is what I came up with for the set of web pages that we were looking at. So we can see here home has nothing but out degrees, so we know that the only time a user visited that page, they came there first. These loops, if someone's going from login to login, that probably means they're refreshing. So if you were looking at something like this and you saw a ton of loops sticking off, that could be a sign that there's a problem. One of the other interesting things is comparing in degrees to out degrees. So if you look at product here, it has an in degree of 3, but an out degree of 1. So that could be a sign that the bounce rate's particularly high on that page. Oops, sorry about that. How do I zoom out? Sorry about that. So if we're looking at product 1, the in degree is much greater than the out degree, so our bounce rate's high. So if we were thinking about what information we might want to store on the edges, we could look at the time between a user visiting the pages, right? So if we had a timestamp for a user on home and a timestamp for a user on login, we could look at the difference and map that as a weight on the edge. So if we were running an e-commerce site and we're trying to find the best ways to shuttle users to payment and eventually success, we can start looking at the weights. So even if they visit more pages, if we're pushing them to that checkout stage faster, that could be a sign that we're making our site better or worse. So that's really one of the interesting things with this. A couple of the other things I want to point out here, you can see product 2 and 3, we have multiple edges in a loop. So that could show us maybe users going back and forth, maybe there's some issue. So if they were on product 3 and it wasn't loading, right, they could go to product 2, then right back, and then refresh. So if we start seeing weird things like that pop up in the graph, it could be a sign that something's wrong. So a lot of you probably recognize this type of problem. If we're running a logistics company and we need to pick something up at the train station, deliver it to all these factories, and then return back to, say, a trucking garage, how can we come up with a graph to represent that? So there's a bunch of different ways of attacking the problem, but the way I came up with to represent it graphically was the only real requirement we have is that we need to go to all the factories in no particular order. So we can't go directly from freight in to the end, but in theory, any factory on the list could be the first or the last one we visit. So if we were going to draw out a graph for this, right, we would know that freight in can't go directly to end, so those would be non-adjacent. But if we were trying to consider the space of all possible paths, everything would be adjacent to each other. And so one of the other interesting questions that comes up here is if we're trying to optimize for something, how can we bring in those edge weightings? So if we're trying to, say, minimize time in transit, distance traveled, gas cost, whatever, we could take historical data and start putting that on the edges. So the graph that I came up with was this one. So one of my other favorite things about this is you can kind of get some cool pictures from relatively mundane scenarios. I didn't display weights on all the lines. I did try that, but it got pretty unreadable pretty quickly. So up here is the only 2 weights you're actually going to see, just so you can see how they would be represented if you were drawing it visually. So every single vertex here is adjacent to every other one, with the exception that there's no edge between freight and end. So in theory, if we had this and we were trying to minimize it, we would want to find the shortest path that visits every one of these vertices, starts at freight, and ends at end. So actually, there's some pretty cool tools in Python we can use to do that automatically. But if we were working on it on a whiteboard, this is one of the ways we'd want to approach it. So one other example I want to show you, and to me, this is the one that looks the least immediately obvious that you'd want to represent it as a graph. So if we're scheduling a conference, and we've essentially made everybody the promise, if you tell me the top 2 talks you want to go to, I guarantee you I'm not going to schedule them concurrently, so you can make it to both. Right? There's quite a few ways you could approach this, but one of the ways we could solve it is graphically. And if you notice, right, if we had an adjacency matrix, we would have these same labels down the side, so it would be square-shaped. This is not square-shaped, so we know that this is not an adjacency matrix. So if that's what anybody jumped to, that's actually not the case here. But one of the things we can think of is if we go down this Bob line, right? So if a 1 shows us they're interested and a 0 shows us they're not, we know that Bob wants to go to E and G, Ashley wants to go to A and C, and so on. So if we're trying to come up with a graph, right, we're trying to look at the relationships between people and talks. There's a couple different ways you can approach it. But to me, the big thing we want to look at is making sure we don't schedule the wrong talks concurrently. So what if we let the talks be the vertices and the edges represented somebody who wants to go to both of them, right? We would have 2 connected talks. show us that the same person wants to go to both. So once we have that, we can actually go back to finding a proper coloring, right? So if two talks are adjacent on our graph, then we know that the same person wants to go to both. So we know that we can't schedule them concurrently. So if we go back and find a proper coloring, we'll know that the minimum number of colors we need to separate those vertices based on what's adjacent is the number of sessions we'd need. So actually this one, you would be able to do it in 2 if it weren't for these 3 that are connected to each other here. So there's a couple different ways to color graphs when you're looking at one. At the moment, there's no guaranteed best way, but I'll talk a little bit about some of the ways we can color them in Python. One word of warning is it can be tricky if you have a really, really convoluted graph and you're trying to color it. So just keep that in mind when you're deciding whether or not to use a graph. So the first 2 graph libraries in Python I want to talk about are iGraph and NetworkX. NetworkX is probably the most popular. That one's written specifically for Python, and it does play nice with the PyData stack. So with this one, you can kind of pass in pandas data frames and stuff, which we'll talk about. But the other big one is called iGraph. So iGraph was actually written for C originally, and it's also available as an R package, a C library, and a Python package. So if you're a little more language agnostic and you basically want to learn one graph package and then take it to the other languages with you, I'd recommend you start with iGraph. One of the big things is that's a little trickier to install, right? With NetworkX, you can just do pip install NetworkX and you're ready to go. With iGraph, there's a couple extra steps, particularly if you're on a Windows machine. That said, it is a little bit more efficient than NetworkX if you're starting to work with really, really big graphs or look at complicated algorithms. One other library I want to bring up is called GraphTool. So this is essentially Python bindings for the C++ Boost Graph library. There's quite a bit of testing data going between iGraph and GraphTool as to which one's faster. My rule of thumb is GraphTool is going to be a little bit faster, at least for everything I've used it for. That said, it is the hardest of the 3 to get set up. And you sort of need to write your code a little bit differently, because if you come in and you start just calling the built-in functions, you might end up not offloading as much work to GraphTool as you want, and you really won't get that C++ speed advantage. So what I'm going to focus on for these examples is actually NetworkX, just because this is PyData, not C data, not R data. But I want you to know these other 2 are out there. So if you're in an environment where little performance boosts are important, you might not want to start with NetworkX. So there's a couple different ways we can share graphs once we've created them. This GraphML versus GML sort of solve the same problem, just one's ASCII based and one is XML based. It's really up to you which one you want to use based on your preference. Like I said, with NetworkX, you can actually pass in adjacency matrices using NumPy or using pandas. So that is one nice thing. Realistically, the other ones will create a graph from an adjacency matrix, but you will have to make sure you convert it or you're going to get an error. So not the end of the world. It's just one more thing you have to worry about if you sort of go too far off the ranch outside the Python libraries. So here's how we would create a graph in NetworkX. So the pretty LaTeX drawings are gone. These are just the matplotlib basic ones. But essentially, right, we'd import NetworkX. The matplotlib is for pyplot. All 3 of the libraries I talked about have a graph class. So when you initiate them, you're always going to call the library abbreviation .graph. And then we can start assigning information to that class as we want to construct the graph. So here you can see we're going to pass it a container of vertices. I just made a list and then added 5 to them. That's another one of the really powerful things here is we can, once we've decided what we want to store as a node, we can run whatever data operations we want, pump them into a list, and then start setting up our graph that way. This command here, add edges from, we pass it what's called an e-bunch. In NetworkX parlance, that's edge bunch. So that's essentially a container of edges. Here I passed it a list of tuples. That's usually the way I do it, but they're pretty loose with what types of containers you can pass them. So you can get a little bit creative with that, just be careful. As far as plotting, we need a position argument here. So spring layout is the one that most people will use by default. With NetworkX, that's sort of some rules as to how to place them. There are other ones you can use though. So I have a circular layout I'm going to show you a little bit later on. But there's quite a few different ways you can arrange it. Realistically, it only matters for visualization. And NetworkX does have a lot of other visualization libraries you can work with. So that's really the only time that's going to be important. For displaying, we also have this draw syntax where we tell it to draw everything individually. So if you forget to call draw, you're going to get a weird looking graph. So for instance, right, if I cut this NetworkX labels line out and ran it, these nodes over here wouldn't be labeled, right? So the 3, 4, 2, 1, 5, those would just show up blank. It really won't affect your operation too much, but if you're trying to sanity check parts of it, you could end up with weird results partway through. So here's how we would store weight on the edges. If you notice the last one, the nodes were all ints. Here are the strings. Any hashable object can be a node. So you have some freedom with what you want to store as a node. And the other thing I want you to look at is here. This is a dictionary. So we can store whatever data we want on these edges. We can store more than one piece. We can have weight, length, width, whatever we want. So if we're building out a graph and we want to start looking at it edgewise, we need to go through those dictionaries. So you can see here, the way I added it was I just put an extra argument at the end. It automatically converted that weight to a string when it showed it to me. But they're now stored as dictionaries on the edges. So in theory, I could just store whatever I wanted down there. So here's the spring layout again. And back here, we're drawing everything. The only real difference is I had to add another draw edge labels line. So one of the other nice things with the draw is this can get cluttered. So if I had length, which I originally did when I was drawing this, it didn't space the nodes properly. So you had all kinds of dictionaries and stuff running over. It can be kind of a mess. And so if you're somebody who doesn't want to spend a bunch of time visualizing it, bear that in mind. So I usually recommend drawing a small one on your own and then doing a couple sanity checks as you go down the line. So say we've already built this big convoluted graph. There are a couple different functions that NetworkX has built in for us to analyze it. So if we call nodes, it's just going to give us a list of all the nodes. We're allowed to mix data types there. Some of the nodes can be strings, some of them could be images, some of them could be integers. So that's just going to spit back a list containing all the nodes. This shortest path, we pass it G, which is the graph object, right, that we created, a start node, and a target. So it's going to go through, it's going to run a Dijkstra shortest path is the implementation in NetworkX. And it's basically just going to find the shortest one. Another word of warning here is if you have two equally short paths, if you just pass it the shortest path function, it's going to only give you one of them. So if it's important to find all the paths, there are a couple different ways you can do it. This might not be the one. And if we call g.degree, that's going to count the degrees on every node and then give us back a dictionary. So here it's a little bit confusing looking just because we have incidents. But realistically, if we mix them, the key is going to be the node identifier, and then the value is just going to be an int representing the number of degrees. So you remember the coloring graph from earlier, right? So let's think about how we would color it a little bit with NetworkX. So if you were looking at scheduling or any sort of concurrency placement, this is the way you'd want to do it. So I didn't show you creating the graph, but this nx.greedyColor is going to use a greedy algorithm to color it. Another little caveat here is if you're working with more complicated graphs, greedy coloring will not necessarily always give you the minimum. In this case, it did, just because it was simple. But the order in which nodes are considered is important. So if you go onto the NetworkX documentation, there's a couple different strategies you can use to order them. I figured that was a little bit outside the scope of this talk, but I want everyone to be aware of it before you start going crazy. This was just me being lazy with a way to count up the number of different colors. But you can see here it did actually the same coloring we did, where F is the odd one out. And so it had 3 different colors. So if we were to run this basically out in the real world, that's one of the ways we could do it. So here's a digraph. This is really where edges become important. So it's going to look out degree, in degree, right? So 1, 2 is not 2, 1 when we're passing in edge tuples. One of the other nice things is we can call, right? We can set it up and just pass a list of edges, and it will create nodes as it sees fit. I've gotten weird results with this before. If maybe I pass it edges that refer to 5 nodes, it'll just add an extra one. So be a little bit careful when you do that. If you notice here, we didn't call nx.graph, I called nx.digraph. There are a couple different types of graphs that we can use with NetworkX. There's multi-graph, which will allow multiple edges. Digraph is directional. There are a couple other ways you can get creative and sort of mix directed and undirected edges, although I wouldn't recommend it. But you can see the graph creation process is almost identical. The only thing I did was change the node size and the font so we could see those arrowheads a little bit. One of the other interesting ones, so as I mentioned, if we start looking for paths through the graph, and it has to respect these arrowheads, if you notice here, number 5 only has in degrees. So we can get to 5, but we can't get out once we're there. So if I call this hasPath function, that's going to give us a Boolean. So if you are looking at website data, you could call this hasPath and see if a user went from one page to the other at any point. And this shortest path basically does the same thing. It's going to give you a list referring to the nodes that you can take for the shortest path through. Those are a couple of the digraph functions. And the last one. So I talked about a matching. I didn't have an example because I was a little bit concerned about time. But if we have one of these bipartite graphs, you can see there's the snip you would make in one motion. This will find the biggest possible matching. So it's just going to return us a set of tuples. And it looks like I'm a little bit short on time, but a couple of the other resources I wanted to point out in case anybody does decide they want to go deeper. Tomorrow, actually, somebody's leading a NetworkX tutorial. So that was kind of a nice little surprise. It's right here in this room, I think at 10 a.m. So if you do want to go hands-on, or you thought I sort of moved through it too fast, it'll be a nice, slower one. So I'd strongly encourage anyone who's interested to check that out. GraphViz was what I used to create the black and white graphs at the beginning. You can run that in Python, but if you just want to practice drawing them, there's actually an in-browser GraphViz you can use, just webgraphviz.com. There is a free graph theory textbook as well. It's going to have a little bit of combinatorics in it. But if you're more interested in the math, that one's licensed in the Creative Commons. You can Google for it, and you'll find it online as a nice little PDF. Graph theory is an area that still has a lot of great work that needs to be done. And unlike a lot of other math areas, there are open problems that undergrads are capable of solving and undergrads have solved. So if you're a little more interested in the academic route and getting published, that's actually a great site to go to, Open Problem Garden. There's a graph theory category. And you can actually output your graphs as TIX packages. So if you're looking to write in LaTeX or anything like that for publishing, all three of these graph packages I talked about will let you produce TIX graphs, so you can embed them directly into your papers. Graph databases are another interesting field, right? It's a little bit outside the scope of this conference. But if you're interested, the biggest vendor, Neo4j, will trade you an O'Reilly book for some personal data about yourself. So if you really want to know, you can go give them your email and where you work and stuff, and they'll send you a free one. There's also a pretty interesting workshop I found. One of the areas I didn't talk about just because it's above my pay grade is language processing. But there's some pretty exciting work going on right now in using graphs to analyze how language is structured. And then lastly, if you're working in a very specific problem area and you're curious about some of the other graphs people have come up with, that site researchgate.net, it's like a social networking site for scientists. Everybody wants someone to read their papers. So there's a lot of open access ones. And if it's closed, you can ask them nicely, and they'll usually send you a copy. So that's all I got. I don't know how much time we have left for questions before the next person has to come in.
We have time for questions, actually.
Oh, cool.
Hey, thanks. I found this really informative. I just had a quick question. So as far as modeling concerns, with Django, it's actually kind of discouraging because it's creates a database, and they say you don't want to alter the database. And so it induces a lot of anxiety, iterating over the design. To come up with some of those models, was that an iterative process, or do you try to draw it out perfectly the first time?
So for these graph models?
Yeah.
Originally it was iterative. After you've done it a few times, you sort of get an instinct and you can start seeing graphs everywhere you look. So one of the things I'd recommend if that's what you want to improve on is go to ResearchGate and look at how people have come up with other graphs. Or if you just Google, graph theory applications for database design or for image recognition, there's tons of people who want you to look at the graphs they've come up with. So it's a really nice sort of open area of math. So there's a lot of cool work you can find out there.
I guess changing it wouldn't affect your database or anything.
It's so in a graph database, would changing the graph affect it? Or was that the question? Or?
Well, just changing the chart wouldn't affect
Oh, it's if you're modeling them in NetworkX?
Yeah.
Depending on what you change. The nice thing is of the packages I mentioned, NetworkX handles dynamic graphs the best. So if you're going to change it sort of in process, I'd recommend start with a small one in NetworkX. And then if performance is a concern, maybe move out to the other ones. But for the most part, changing stuff isn't terribly difficult.
Very good. Thank you so much.
Anybody else?
Thanks. That was really interesting. Do you have this sort of maybe outside of the Python sort of scope, but do you have any experience with graph query languages or ways to query graph databases?
Yeah. So the one I've used the most as far as graph databases is Neo4j. They have their own query language called Cypher that I've spent quite a bit of time fighting with.
Okay.
It's actually kind of interesting. They have a little arrow syntax so you can follow the edges through. That's where I'd recommend starting just because there's the most information about it. But Cypher is the only one I've used, although there's a bunch of other ones.
Maybe anybody else for any more questions? Oh, maybe the last one.
Hi, great talk. it seemed like there's an awful lot of intuition required in choosing, what's going to be a node, what's going to be an edge. If you were talking to someone like myself in a situation where maybe I know what my nodes are, but I've got 200 or 300 different flavors and options for edges. Any advice there?
Yeah, so there's no universal rule that I know of I can give you. One of the things I'd recommend is if you're working within a very specific space, look at what other people have done. So a lot of these graphs follow similar patterns, right? So for me, I was working in logistics most recently, so I pulled ResearchGate papers on other stuff people have done in the logistics area. I was able to get some insight. Usually, if you're thinking about that object relationship model, the relationship in question is what you'd want to use as an edge. So, beyond that, you kind of have to play with it. But if you do it a few times, you'll quickly see what's reasonable and what isn't. But as you get down to more specific areas, there's rules of thumb. Yeah, sorry, I kind of motored through it because we had IT trouble at the beginning. So if there are any other questions, I'll be lurking around. Feel free to come grab me. I love talking about this stuff, so I'd be happy to answer anything on the fly.